Hello, and welcome to this video about gravitation. I'm Bob, and I will be your guide. In today's video, we are going to talk about a few physics phenomena that may seem quite obvious, but are sometimes misunderstood. Gravitation is the most important force on the scale of planets, stars, and galaxies. The gravitational force is actually one of four fundamental forces that rule the universe, along with the electromagnetic force, the strong nuclear force, and the weak nuclear force. The gravitational force is considered the weakest of the four interactions at the atomic scale, but on large scales, gravitation has immense effects. It is responsible for holding our Earth together and for keeping the planets in orbit about the Sun. The gravitational pull of stars makes it possible for them to maintain their own integrity, while nuclear reactions are taking place at their core. These reactions generate the Sun's energy output, which makes it possible for life to exist on Earth. Today, I will try to explain the theory of gravitation as Newton formulated it. We will see a way to observe this gravitational force. I will then introduce you to a few phenomena that can be explained thanks to the law of gravitation. Finally, we will see how all those things combine to make it possible for entire planetary systems to exist. Born in 1642, Isaac Newton was a British mathematician, physician, alchemist, astronomer, and theologian. Newton published his theory in 1687 in his book named Philosophia Naturalis Principia Mathematica. What does it exactly specify? That's what we are going to see now. The law of universal gravitation states that every particle attracts every other particle in the universe with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their center. This translates into this equation. Let's take a closer look. Fg is the magnitude of the gravitational force acting on either particles. It is expressed in newtons. Those particles have masses m1 and m2, measured in kilograms. D is the distance between the particles in meter, and G is a fundamental physical constant called the gravitational constant, but we will come back to it later. We should make two important comments on this law. First of all, it is essential to know that we can only use this formula for isolated points. Secondly, notice that we use the term mass and not weight. These two words refer to two different concepts that are often misunderstood. The mass represents the amount of substance contained in an object. It is a scalar, which means that it is a number that has no direction and doesn't vary with the object's location. The mass unit is a kilogram. On the other hand, the weight is a force, which is measured in Newton. The weight of a body is the total gravitational force exerted on the body by all other bodies in the universe. But when the body is near the surface of the Earth, we can neglect all other gravitational forces and consider the weight as just the Earth's gravitational attraction. This force is always in the direction of the planet's center. Let's illustrate that difference. I have a mass of 70 kilograms on Earth, and I weigh approximately 687 newtons. If I were to go on the Moon, my mass would still be 70 kilograms, but my weight would be less, only about 114 newtons. That is because the gravitational force between the Moon and me is less than with the Earth, which is more massive. Let's come back to the equation of Newton that we just introduced. We talked about the fundamental universal gravitational constant, g. We know that the gravitational force Fg is a force that attracts two particles of mass m1 and m2. This force is inversely proportional to the square of the distance between both particles. So g is an unknown constant that needs to be found. The value of g has been found by Henry Cavendish with his famous experiment. Henry Cavendish was a British scientist born in 1731. At this time, the radius and mass of the Earth weren't known, and Cavendish wanted to find the density of the planet. Therefore, it was capital for him to approximate the value of g at his best. Cavendish devised an experiment using a torsion balance that does just that. G has been measured by Cavendish in 1798. Its value is approximately 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Cavendish hung two small spheres to the end of a torsion balance, a device that can rotate very easily under the influence of even very weak forces. To capture this movement, a mirror is attached to the balance, which will reflect a laser beam onto a scale. Once the system is stabilized, Two heavier spheres are placed near the small masses. The torsion balance twists of a certain amplitude due to the attractive gravitational forces. The small spheres are attracted by the large ones. This angle is measured by the displacement of the laser on the scale. Here you can see my own attempt at the experiment. We can clearly see that the balance is moving after adding the masses. One can very easily observe objects falling. There is a gravitational force between any object and the Earth. This force pulls the object to the ground. Intuitively, we tend to think that the heavier the object, the faster it will fall. But that is wrong. Let's take a simple example. Look at those two identical bottles falling. The first is full of water and has a mass of 1 kilogram. The other is empty and has a mass of 0.2 kilogram. The standard misconception is to believe that the heavier bottle will accelerate at a greater rate and touch the ground first. However, we see here that both bottles were dropped at the same time and touched the ground at the exact same moment. While the gravitational force exerted on either bottle is not the same, they are falling with the same acceleration. We know that the resulting force acting on an object is equal to the mass of the object multiplied by its acceleration. Here, the only force acting on the object is the gravitational force. Thanks to those equations, we can write this and simplify the mass. We find the acceleration A equals g times me divided by r squared, where me is the mass of the Earth and r is the distance between the object and the center of the planet. A does not depend on the object's mass. It does, however, depend on the mass of the planet and the distance of the object from the planet's center. This acceleration due to gravitation is called gravitational acceleration and is usually denoted by lowercase g. We can input the values for the radius and mass of the Earth, and we find that when we're near the surface of the Earth, the gravitational acceleration is approximately 9.81 meters per second squared. Now, what if instead of just letting the object fall, a horizontal velocity was given to it? Gravity will only affect the vertical component of the trajectory. If an object is propelled from a certain height with some horizontal velocity, gravity will act on the object and pull it towards the surface of the Earth. If we neglect air resistance, the object will keep its horizontal velocity as a gravitational force only acts vertically, that is, towards the ground. The object describes a parabolic trajectory before it falls to the ground. If we increase the initial velocity, the object will fall further and further. When considering larger scales, the curvature of the Earth must be taken into account, and the direction of the gravitational force is not just vertical anymore. It changes as the object moves. The object is always attracted towards the center of the Earth. The trajectory of the object is better described as elliptic. If the planet was reduced to its center of mass, the object would fall around it, following the shape of an ellipse. As the initial speed of the object increases, the size of the elliptic trajectory increases as well. At some point, the speed will be such that the object will never touch the Earth's surface again. The object is then in orbit. The object is constantly falling around the planet. If we increase the speed some more, it will describe a circular orbit around the Earth. If the speed goes even higher, the object will describe a larger ellipse. And finally, when the velocity is too high, the ellipse will be open and the object will never come back to Earth. Can an object ever escape the gravitational hold of a planet? It is possible to calculate the speed you have to give to an object so that it will never come back to the planet. This speed is called the escape velocity. To find the escape velocity, we need to remember the principle of energy conservation. Technically, I have to give an initial kinetic energy to the object such that it will overcome the gravitational potential energy entirely, and the total energy will be zero at infinity. Solving for v, we can find the escape velocity. V equals square root of 2 times g times me divided by r. Satellites are a good example of circular orbits. In a circular orbit, a satellite is kept at constant speed at a constant distance from the planet by the gravitational force acting between them. The satellite is in a uniform circular motion, and gravity acts as a centripetal force. This force is directed towards the center of the Earth and hence towards the center of the orbit. As we can see on this graph, the net force, which represents the gravitational force, and the centripetal acceleration are in the same direction. Thanks to Newton's second law, we know that the sum of forces is equal to the mass multiplied by the acceleration. So, g times me times m divided by r squared equals m times v squared divided by r. Solving this for v, we find v equals square root of g times me divided by r. With this formula, we can clearly see that the motion of a satellite does not depend on its mass, but rather on the radius of the orbit. This means that we can't choose the orbit radius r and the speed v independently. So if we want to launch an apple or a shuttle on the same orbit, they will require the same velocity. I have told you that objects in orbit travel around the central body in an elliptic trajectory. This realization came from 17th century mathematician and astronomer Johannes Kepler. Through trial and error, Kepler discovered 3 laws that precisely describe the motions of the planets. The first law states that each planet moves in an elliptical orbit with the Sun at one focus of the ellipse. This figure shows the elliptical orbit described in Kepler's first law. The longest dimension is called the major axis. The characteristic of an ellipse is that the sum of the distances from S to P and from S' to P is the same for all points on the curve. S and S' are the foci, with the Sun on the S point and nothing at the other focus. The second law of Kepler states that a line from the Sun to a given planet sweeps out equal areas in equal times. If we draw a line from the Sun to the planet, this line will sweep out a certain area as the planet moves. What Kepler's second law means is that for the same time interval, this area is going to be the same at any point on the orbit. When the planet is close to the Sun, the distance r between the planet and the Sun is small, and the distance traveled by the planet must be large. And when the planet is far from the Sun, r is large and the distance traveled is small. What this essentially means is that the speed of the planet increases as it nears the Sun and decreases as it recedes from the Sun. Finally, the third law states that the period of a planet is proportional to the 3/2 power of the major axis length of its orbit. The period is the time it takes for a satellite to complete one revolution at a certain speed. In other words, t is the orbit circumference divided by v. For example, for a circular orbit around the Sun, we have v equals square root of g times ms divided by r. We can easily find t equals 2 times pi times r to the 3/2 divided by the square root of g times ms. We see that the period is proportional to the radius to the 3/2. This is true also for ellipses other than a circle, with the orbit radius r replaced by the semi-major axis a. T equals 2 times pi times a to the 3/2 divided by the square root of g times ms. A common misconception is that astronauts in space undergo a phenomenon of zero gravity, but that is a myth. Imagine I were an astronaut on board the International Space Station. I would then become a satellite of the Earth myself. The Earth's gravitational attraction holds me in the same orbit as the station. We have the same velocity and acceleration. There is nothing pushing against me that would make me feel my weight, because the station and I are falling at the same time. I am in a state of apparent weightlessness. This phenomenon can occur whenever gravity is the only force to interact, and not only in orbit. For example, apparent weightlessness can be experienced inside a plane that follows certain parabolic trajectories. This can be replicated on a smaller scale when we launch this transparent box with Lego pieces inside it. Of course, here gravity is not the only force to interact, since there is the air friction, but we can neglect it. The Lego man doesn't touch any walls because the Lego and the box both fall at the same time. The Lego man is in apparent weightlessness. We have seen how gravitation can explain the motion of sole objects orbiting a planet or the Sun. But gravitation is key in maintaining entire planetary systems together. It's gravitation that makes the nuclear reaction happening within stars possible. And it's gravitation that rules the trajectories of all the bodies orbiting the star, and of the satellites orbiting those planets. In 2015, a team of Belgian astronomers discovered a system of 7 planets orbiting an ultra-cool red dwarf star. This system is called TRAPPIST-1. Here you can see a model of this system. It is important to understand that the planets are not only attracted by the star in the center of the system, but there is a gravitational force acting between any 2 planets as well.